Just have to caution Abby that I have the super soaker where you freeze the core so it makes super cold water when you. So first of all, the hook is gonna come out long before this talk is finished. That's okay. And I first of all wanted to thank George for his great, saving my life at Las Campanas because of my driving skills at Las Campanas, particularly after the road. I almost drove on the concrete before it was set, and then there were many mistakes with the snow and anyway, it was a lot of fun. Driving lessons on Las Campanas were great. And then the other story that I have about George is, and congratulations, by the way, that Alan Dressler was complaining about people talking in the halls, because you're trying to concentrate and there's all these conversations going on, excited conversations. And so when George was director here, Alan mentioned this to him, and George put up a sign that I wish I had saved. He said, please be careful not to talk so loudly in the halls because people in their offices are thinking or sleeping great thoughts. Okay, so great director, So, okay, the hook is going to come out very soon. Basically, Abby has done a beautiful job of looking at individual fields and looking at the variable star content in those fields. This is a survey of the southern bulge, and it's now soon the northern bulge, although our first 4 nights have been clouded out this year. But we do hope, I've been used to lecturing through a mask for the whole semester, but it's so much easier not to lecture through a mask, so I'm going to take it off. So we basically, well, let's see, we basically did the survey of the southern bulge. This is the ECAM. I'm sure you've seen all this, so I'll skip through it. And in fact, there's been a number of talks showing this kind of thing. Here's the field of regard, which is most of the mass, so plus or minus 10 degrees. So Abby's fields are on the far side, but we get that whole area because we want a contiguous area, plus 2 fields that are centered on the Sagittarius dwarf spheroidal. All of these globular clusters are in our field. In Christian's paper, you can see beautiful color magnitude diagrams and analyses of a number of those clusters. And this just shows the reddening and with our fields superimposed, and an effort to show that we get most of the 2-micron mass of the southern bulge, or much of it, encompassed in our survey. Anyway, I'll skip through some of this, but basically there's been a number of great people involved, including Andrea Kunder, who's here, who was really a leader in getting our first data set going, and especially Scott Michael at Indiana University, Katie Pilichowski for providing the computing support for the project, which is like 50 terabytes of data. Then, of course, here's Andrea and Justin Cater, who's a student who's working on the globular clusters, and Christian Johnson, who is the hero because he wrote the code to reduce all of this data, point spread function fit with DAO FOT, this entire data set in 6 passbands. This just shows his analysis, and I'll skip through this, but basically much of our data was taken in non-optimal conditions when it was not photometric, and we had to transfer the photometric solution to different fields, which was a lot of work. All the fields were interlocking and overlapping. This image on the left here actually shows the bulge, but with comprised of density maps of detected sources, not an image of the bulge itself. So it's a contiguous structure. I'll skip through this. We've used the Simeon reddening map, which is 1 arc-minute by 1 arc-minute square. So our goal is to get everything on a common reddening scale. And we're doing one of the advantages, because we have short exposures, we even get good photometry for the brightest stars. You see DCAPS and PAN stars, which are 2 other surveys that cover this field, don't have quite as good photometry, and they also fail on the most on the brightest stars.
The red bars, the red strips.
Oh, those are the BDBS photometry to compare. So the red, so in red is our photometry, and it's just basically showing that how well we do compared to the others. Or wait a minute, I'm sorry, the red is actually NGC 6522, a metal pore globular cluster that is in that field. I'm sorry. That's what that red is. That NGC 6522 has a very blue horizontal branch, excuse me. And this just shows some of our fields. So we get good photometry over the entire bulge. That was the goal, is to get good photometry in all these colors, de-redden over the entire bulge. And then this shows that you can match with Gaia, and this is getting better. This is a match with DR2, but you see, you get down quite faint with well past the red clump with good matching, and this is for good Gaia, getting both the proper motions and parallaxes for stars that are within 3 kiloparsecs. That will get better over time. Sorry, Abby, yes, I do show this plot, and I argue that, so what is a blue loop star? It's a very luminous star, supergiant, right? So in fact, they must be intrinsically luminous, and therefore, in fact, blue supergiant isochrones pass even more luminous than that feature. So if these stars are in that phase of evolution, they must be very, very distant. However, when one looks at their distances in green, according to Gaia, they're very nearby. So obviously, the other thing that we've done is we've actually looked for turn-off stars younger than 2 billion years over the whole bulge, and that will be the end, which I don't think I'll have time to show you, but we also don't find evidence of a young turn-off to support the evolved, our 1 gigayear, more or less, turn-off to have blue supergiant stars. Now, Gaia is very powerful. There will be more things coming. Here, this little dot there in the vector point plot, that is the Sagittarius dwarf toroidal galaxy in the vector point plot. And then this is just another interesting object. FSR 1758 was thought to be some kind of dwarf toroidal galaxy, but it's actually a metal poor globular cluster. You can see the, see if I can use the laser guide star here. Yes, there's a blue horizontal branch and red giant branch, so metal poor globular cluster. A lot of globular clusters have been discovered in the bulge. Mineti 22 gets its own paper in AppJ. Unfortunately, it doesn't quite make it here in the vector point plot, nor when you look at, it doesn't seem to be present in our field. It doesn't seem to be present in the color magnitude diagram. No hits, no runs, no errors, no men left on base, no globular cluster. Similarly, for a lot of these other clusters, sorry, you have every right to, here I am attacking all these people. I say, I wonder why people don't like me. Oh, well, maybe it's because I should be nicer. And it was very pioneering of Dante to propose these clusters, but it's very important to actually confirm, what the truth is. That's what science is all about. And for example, in the metallicity distribution, this is Bensby's metallicity distribution, in which there are, these are from this one is from the microlens dwarfs, and then possible multiple peaks, which have important inferences in terms of understanding the chemical evolution of the bulge. There are also a tendency to have, this was the work of, to decompose into various Gaussians in this study. I like to say that, in terms of decomposing a distribution into Gaussians, I like to use the Martini rule. 1 martini is great. 2 martinis, you can be pretty happy on 2 martinis. More than 2 martinis, not a good idea. Too many Gaussians, too many martinis. But so we wanted to look at the abundance distribution in an unbiased way, not decomposing into Gaussians, but just measuring metallicity. And we noticed, actually, Christian noticed, that the U band is extraordinarily good and remains sensitive to metallicity. This showing with the large numbers of iron lines here. It remains sensitive to metallicity, even to solar metallicity and higher. So you can use U minus G and U minus I as potential measures of metallicity in the bulge. Yeah. These would be for, roughly 4 to 5,000 Kelvin. So these are like red clump stars. Say not our Lyrae temperature, but just, red giant, red clump stars. So these are red clump stars. And what Christian did was to match these with Szalkali's measurements in of Fe over H at high resolution. So you get a correlation between U minus I naught and Fe over H, very nice correlation, with a 0.2 dex scatter. Unfortunately, our NSF reviewer thought that this was just far too much scatter, but remember, this is a photometric metallicity calibration, and you're getting metallicities of 3 million stars using this method. So here are different fields. Yes?
What's going on with the metal rich end? The little points are not.
Yes, in this field, let's look at the other fields. I think there's a little tendency, I think that honestly, the next phase of our effort will be to do an SED-based de-reddening, or try to do a more sophisticated simultaneous reddening and metallicity solution. And I think we will do better. I think this is, I don't think there's nothing perfect, but it's reasonable. In fact, here, this plot might convince you a little bit. This is BDBS metallicity. That's the photometric versus spectroscopic metallicity. And here, there's not such a dramatic tendency to deviate in, it's acceptable. And in fact, here's a distribution. Here's the Gibbs spectroscopic in red and the photometric in gray. So it's not bad, given that it's what you're trying to do. We fit it actually to an elephant here. I don't know if you've ever read The Little Prince, but you see if the python has eaten the elephant, you get a very good fit to this distribution. But actually, so what we're doing here is comparing the metallicity distributions to the Gibbs spectroscopic metallicity distributions. And the gray is the photometric. And what you notice seriously is a one zone model-like shape here. At low latitudes, this is -4 and -6 and -8. And then you see by -8, the distribution completely flip in its shape to a shape that I don't have a physical explanation for this shape. But there does seem to be two general metallicity distributions. And in fact, now with 2.6 million red clump stars, and this paper has just been revised, so it should be out soon, you could see that at low latitude, you have the roughly simple one zone model, and then you have other peaks emerging. And then finally at -10 degrees, you get this different shape, which we have not yet interpreted. And this is now sorting by, rather than degrees below the plane, this is by distance below the plane. Remember, red clump stars, you can get a 10% distance to a red clump star. So these are in the bulge. So you could see the shape of the abundance distribution changing with galactic latitude from this shape here to this very different, peaking at about -0.5 dex. And I'll skip through this, but and this also shows kind of the same thing where you're grouping by distance below the plane, and now going in strips of galactic longitude. And you could see that the main takeaway from this is that there is very little change in the abundance distribution shape in galactic longitude, whereas there is a dramatic change in galactic latitude. We can also define these parameters in the shape of the distribution. For example, the half width toward the metal rich end, the separation of the peaks, the position of the metal poor and the metal rich peak. And we can then look at how these parameters change as a function of galactic latitude. And you can see that the metal poor declines away, the metal rich. This has been seen in a number of studies that the metal rich peak tends to stay the same toward the plane. And then finally, the metal over here, this half width parameter increases toward the plane. In fact, you get both more metal rich and more metal poor stars quite strikingly toward the disk. So there's quite a tendency for the metal rich stars to be concentrated toward the plane, which has been seen in other studies. And then we can map these physical parameters out here. This turns out to be an area where there's a peak width and velocity dispersion. So we map all those things, and what you could see is that there is a dramatic change in latitude, very little change in galactic longitude. And this shows the velocity dispersion in L velocity increasing here toward the plane, done by Tommaso Marchetti. So we're seeing this tendency. So we favor kind of, so what is the story with the abundance distributions? Well, we favor kind of two martinis, one distribution that pertains to the plane, one distribution that pertains away from the plane, and then kind of a hybrid of the two distributions, but they're not Gaussians. Okay, so, and the simple model fits decently near the plane, though there's a little deficit at both the metal rich and metal poor end. And this figure reinforces the striking tendency of the metal rich population to concentrate toward the plane. So here's the most metal rich stars. And then as you move away and move down in metallicity, you don't see a lot of change, except here you almost see this little peanut-shaped bulge feature. And then you see a kind of a vertical broadening as you get to lower metallicity. And this feature, this thing, and I realize I apologize, there's a lot of confusing plots. But the main takeaway is that at all galactic longitudes, the metal-rich stars are steeply concentrated to the plane, increasingly so with higher metallicity. But there is very little change in galactic longitude. So galactic latitude, big change, galactic longitude. So you think of the possibility of the bulge having formed from the buckling of a thick disk, and maybe there is some idea of preserving the structure of the disk in the sense that the gradients are most important going away from the plane. Here are some of our first efforts at trying to fit to various chemical evolution models. And the basic thing here is that you can look at it in two different ways. One is that you have the simple model close to the plane and a mass loss model that tends to fit decently well away from the plane. That is a wind outflow model away from the plane. The other way to look at it is that the thin disk, kind of a thin disk like abundance distribution, fits close to the plane, and a thick disk maybe further away from the plane. The interesting thing, though, is going back to Brava, that even though there's this dramatic change in the abundance distribution away from the plane, there is not a dramatic change in rotational kinematics. Now, we're going to look at the data. We're just about looking, since we have the red clump stars, they all have Gaia proper motions. We're going to see if we can detect any significant change in kinematics as a function of metallicity. But you do see in galaxies like M82, there's evidence of wind outflows, and very possibly outflows have played a role in the formation of the bulge and the establishment of the abundance distribution in the bulge. Also, and this is the point I made earlier, here is kind of a metallicity map based on Christian Johnson's bulge red clump metallicities. And this is the Zoccoli map. And we just argue that they're at Fe over H 0. There is not a dramatic change in the shape. And I can reinforce that by going back to here. You see here is Fe over H of 0. And there is not a dramatic change from a disky to a round distribution, although there is a progression perhaps. It's that we just haven't wanted to look at it that way, because why should there be a physical break at solar metallicity where the structure changes so dramatically from disky to spheroidal. And then I'm going to talk briefly, but there's not much time, but what we have done is to examine, so one of the goals is to make as many enemies as possible. No, I'm sorry. But there is the Bensby claim for these dramatic number of metal-rich stars that are also as young as 1 gigayear. So we decided to take the Bensby results, and led by Meredith Joyce, the Lasker Fellow at Space Telescope, to do an analysis of these log G and log T effective for the microlens dwarfs using the missed isochrones. And so she did this analysis and, comparing to Bensby's original work, and the new work tends to find older ages. So what you have here in red is the original Bensby et al. Work, which is very significant because it says that for stars above solar metallicity, there is a large number of young, perhaps massive stars. In fact, massive enough to make blue supergiants, right? So there could be blue supergiants. And we must be open to the possibility that there is a large population of massive stars because, in fact, there are a number of luminous AGB stars in the bulge with intrinsic luminosities up to -6, -7. So there is but you don't know the distances that well. So the thing is that with the new ages, we lose this tail, much of this tail above younger than 5 gigayears. We have a couple of stars, but we now find most of the stars push. There does seem to be a contingent of younger stars at higher metallicity. And so, in fact, I'm making the point that perhaps, and let me know when time is up. So, okay, so perhaps these younger stars are in fact telling us that, to have this dramatic concentration of metal-rich stars toward the plane implies that indeed they may be younger. There may have been, there may have been something in the formation history that favors perhaps there's a star formation in the plane at the metal-rich end that is populating this end, this tail of, stars in the 9 to 7 to 5-ish gigayear range. So it's something that our minds are open to. So what we have done to kind of take another look at this is to use Gaia to clean this color magnitude diagram of foreground stars to the best ability that we can. And this is really the brilliant work of Tommaso Marchetti at ESO. And this uses a technique first developed by Kuiken and Rich, and then really well done by Clarkson et al. 2008 and others, the Bulge Treasury Survey, where you use the mean proper motion to veto the foreground disk population from the color magnitude diagram. So you do this and you can get rid of much of this foreground blue plume population. And in addition, you could do other things, but to try to do it by color as well. And in the end, you can overlay isochrones and you can look for potentially young isochrones like this 1 gigayear isochrone. Now looking over the whole of the field of regard of BDBS. And you can see that while you can't really totally rule out 2 gigayear stars, you can pretty much say that there are precious few stars younger than 2 billion years. And this will only get better as Gaia gets better and so on. And this shows all the color magnitude diagrams that we have. The referee didn't like that plot, but we're also looking at the red giant bump as another constraint. Still very much a work in progress. And then finally, we are able to use the U-band to look at multiple populations and globular clusters. This paper will be forthcoming soon, but we are able to see a very good correlation between globular cluster luminosity and the presence of second generation stars in globular clusters. And that basically wraps it up. And sorry it's gone by so quickly. I know it's a lot of stuff. So anyway, I'm done. And thank you, George. You know, I don't know if I'd be around if I hadn't had that very solid advice from Las Campanas director, George Preston, on not driving my car off the edge of the cliff.
There's one very serious bias in your survey.
Mm.
You should be able to tell me immediately what it is. Why do you have no stars, more metal poor?
Oh, yes, of course. I can tell you right away why we have stars more metal poor than -1 Dex, because we're looking at red clump stars.
Yes. and
That's
so you're-
exactly right. Yes,
and so you're
I know.
modeling what's there and what's not is, you know,
Well, you know, there have been some beautiful, like Aronson et al. The pristine survey has, and of course, actually, speaking of pioneering work by George Preston, the -10 degree field in the bulge, where numerous interesting stars of interesting chemical complexity have been discovered. Andy McWilliam and Andreas Koch and others wrote a very important paper on those stars. But we can't, we don't, you know, we could make the argument quantitatively that they are a very small contingent. The
no,
bulk of the
no,
bar.
at 10 degrees above the
Ah,
plane,
yeah.
it the stars dominate. The stars at -1 and a bit less, -1.2. That's where the peak of the distribution is.
Well, we have to, I mean, you know, we will
Another
certainly,
test.
I'll look into that.
Another test,
But
number of giant stars to number of stars in the horizontal branch. You would find.
yeah, yeah, I would say though that what we're seeing in the change of the distribution is kicking in at -6 degrees, where the bulk of the mass is still dominated by the bar and by this main population, I would argue. So you know, we'll take another look at -10 degrees, you know, and check for the extreme blue horizontal branch that should be there that we have not seen that much of. But we will take, we also, the other thing
That
too.
is one magnitude diagram. Blue horizontal
Yeah, there
branch.
is, yes,
I
there's
don't know
a
what
blue, no, we see it. It's just, we argue that the number of red clump stars vastly exceeds those blue HB stars.
Sure.
Yeah, so we're still getting a picture. What we want to do is get a picture of what the population more metal rich than -1 Dex is doing. But if you look at the published abundance distributions of K giants and so on and so forth, there is a tail, there's almost nothing. If you look at just look at Zoccoli's papers or any of the, you know, back to Rich 88. I mean, there's very few stars in an unbiased red giant survey more metal poor than -1. That doesn't mean that the population of stars in the bulge below -1 is not fascinating and important. They just aren't numerous. We will, you know, look at that question. You raise an important question, and we will make sure to really re-examine it. I realize that we have a point of disagreement, which is good, and we will very carefully, you know, address it. So that's all I can say. I don't think it's a problem below -8 degrees.
We've got
No, not.
Abby
Yeah.
and Anna.
Right, Mike. So, well, we can grant that the question of what the blue plume stars are may be controversial. I take exception to your remark about that they're too faint and therefore have to be at great distance. The luminosity of those stars depends on their mass, and they can be as low as just arising out of the clump. So the one that Vern looked at is perfectly consistent with a mass of 2.5 solar masses, is perfectly consistent for where it is on that diagram.
Well, I would just recommend, you know, checking the Gaia parallaxes for those stars because they are very
I don't
luminous.
trust the Gaia parallaxes at
Okay.
7, at
Well,
a distance of 7 kilometers.
No, but we're showing that most of the stars in that
that's a
plume
different
are
argument.
closer.
That's a different
Okay.
argument. But these can be at the brightness that they are, if they are, blue plume stars are helium burning.
Well, they don't spend much time at that low luminosity. I'll tell you what, you know, we'll have, yeah, what mass do you think they are? Because actually, Meredith will run those isochrones. What mass do you think we should be looking at?
Mike?
Okay, we have none more questions.
Yes, it is quick. So Mike, about the potentially new globular clusters in the bulge that were reported,
Yeah,
like,
yeah.
have you find evidence of any of them like being actual, like
Not-
detecting them in your data, or are they all kind of ruled
I think
out?
some of the new clusters that are at lower latitudes that are more highly extinct and are in fact real. We're having another look at some claimed clusters, but so far nothing turned up. For example, one of the things we did very early on was to look for clumps of BHB stars to see if we could pick up a metal pore cluster or two, and we didn't see anything. But no, at the moment, we're not confirming any of those
Oh,
clusters.
none. Oh, wow.
Not at the moment, but
Okay.
we're having another look with, the EDR3 data, and, we're going to have a definite deeper look. But unfortunately, our survey does not reach below -2 degrees.
Okay, we should move on. Let's thank Mike again.